These earth and stone dikes seem like overkill, especially when the sea is so calm below. But in 500 years of trying to conquer the sea, the Dutch have learned a hard lesson. Overkill is necessary for one reason only: severe storms. 1953, the coast of Holland. High winds pushed the tide 16 feet above normal, enough to overwhelm the dikes that existed at that time. Frantic efforts were made to stop the sea from surging inland, but its force was too powerful, and the country suffered terribly. Nearly 2,000 people died in this tragedy, and the survivors vowed never to let it happen again. The cost of fulfilling that pledge was staggering. According to Pier Valinga, Holland's leading authority on dikes and sea level rise.
After the 1953 storm, we had to heighten the dikes by about 2 to 3 meters, and that cost over $10 billion. And that's, well, in the order of 0.5 to 1% of GNP on an annual basis. And, well, that is a continuous amount. It's not just construction, but it's also maintenance, the dunes and the dikes, and it comes back every year.
Constructing dikes is serious business on the scale of building a first-rate national highway system. Wealthy, developed countries could perhaps afford to follow in Holland's footsteps. But in developing countries like Bangladesh and Indonesia, the expense would be out of reach. Money isn't the only issue either. As well as laborers, thousands of skilled designers and engineers are required to do the job. In countries that don't have these resources, vulnerable coastal towns and cities might have to be abandoned. Either way, building dikes or abandoning valuable land, allowing the sea to rise will mean a tremendous waste.
When the sea level will rise, as we expect now, we must do the same thing again, and it will cost another 10 billion or even more. And, well, technically it's possible, but it's such wrong way of spending money, I would say. We could better invest that in keeping down the rate of climate change.
If we don't keep down the rate of change, humans won't be the only ones to suffer. Take the famous Florida Everglades National Park. Much of this ecosystem depends on its connection to salt water, so walling off the sea makes no sense. But to biologist Larry Harris, the alternative also spells disaster.
If the projections are correct, the sea will come up about 1 foot within the next 25 to 40 years. That means that the edge of the sea that we're standing on today will occur 10 miles north of here by about the year 2010. And if the sea level comes up 2 or 3 feet, then the entire park will be lost. And we fear that Everglades National Park may be one of the first national parks lost from the face of the earth.
At stake here is a treasure chest of unique and endangered wildlife, including countless species of rare wading birds. The American alligator, the manatee, an ancient aquatic cousin of the elephant, and the Florida panther. They live in a closed-in world, quite unlike the time when the Saharan monsoons disappeared, when people and animals had plenty of room to move. If the park is squeezed smaller by rising water, these animals will be forced up against an insurmountable barrier, which stands between the Everglades and other wetlands lying to the north.
The animal species, of course, would normally be able to move up the peninsula if there weren't human habitation and human blockage. But with all of the interstate highways and the chain link fences and barking dogs and golf courses, the wildlife will be caught between the devil and the deep blue sea.
A completely different problem will plague animals in wild areas away from the coast. In many cases, the plants and trees they depend on for survival only grow under specific regional climate conditions. that have been stable for thousands of years. But computer climate predictions show entire temperature and rainfall belts shifting several hundred miles by the middle of the next century. The only way for vegetation to survive is to follow. Plant species can move up to a half a mile a year, as their seeds are blown by the wind or carried by animals. But just as in the Everglades, most wild places are hemmed in by towns, cities, and farms, so there won't be any escape route. Unless we actually pay for massive relocation, forests could end up looking like this, as they get marooned in the wrong climate. And of course, the animals depending on these forests would be trapped at the same time. And then there's the entire world's food supply. It's also threatened by rapidly shifting climate patterns. A disturbing example of what high temperature and reduced rainfall can do to food crops was the American drought of 1988. That summer, the grain harvest was devastated by the unusual weather. Because grain dealers still had stockpiles from previous years, which they nearly emptied, consumers hardly suffered at all. But what if there had been another bad harvest the next year, and then the year after that? To Lester Brown, president of the World Watch Institute in Washington, this is a scenario we're likely to face if we let global warming continue.
When stocks are so low, the world becomes very vulnerable to another short harvest. And as we look ahead at the prospect of more and more hot summers, like the summer of '88, the future food security of the world is becoming more and more questionable. We could see food security replace military security as the principal preoccupation of many governments in the world during the 1990s.
Food crops are extremely sensitive to weather. It doesn't take a whole summer of heat or drought to reduce yields severely. In the case of corn, for instance, just a few 95-degree days in the middle of the growing season can ruin the harvest. For corn to develop, pollen must fall from the top of the plant onto the silks below. Each silk corresponds to one potential kernel on the ear of corn. Silks that fail to catch pollen usually result in missing kernels. Here's the problem. If the temperature hits 95 degrees, the leaves of the corn plant curl up to conserve water, covering the silks. Now, when the pollen drops, many silks won't get any. Worse yet, if there's a hot spell a little earlier, the silks won't grow, but the pollen will. So they can end up missing each other altogether.
When that happens, you can get a severely reduced corn harvest. Corn is important because it accounts for 2/3 of the U.S. grain harvest and 1/8 of the world grain harvest. When the U.S. corn crop is sharply reduced as it was in the summer of 1988, the entire world feels it.
If climate gets consistently warmer, corn production might have to shift to Canada, without American farmers, of course. But that's easier said than done. One of the factors making America's corn belt so productive is deep, rich soils, and the thin soils of Canada aren't nearly as good. Growing the same amount of corn there would cost much more, if it were possible at all. It's true, some agricultural zones might benefit from global warming. For instance, much of the best land in the Soviet Union is underused today because the weather's too cold. But there are many more regions where agriculture would probably suffer, like Southern Asia, where coastal rice production could be ruined by salt water flooding from the sea. In effect, we'll be playing roulette with our food supply if we allow the climate to change.
The evolution of agriculture, reaching its current level of productivity to the point where it will support 5.2 billion people, is closely keyed to the existing climate system. We have no guarantee that if that climate system changes, we'll be able to feed 5.2 billion people as we do today.
To make matters worse, there will be around 10 billion people to feed by the year 2050, if the world's population continues to grow at its present rate. This would create twice the demand for food at the same time supplies are threatened. In a greenhouse future, other vital resources we depend on, like water, may no longer be available where we're accustomed to having them. Will we be prepared to deal with the consequences? What, for instance, would we do if the water coming down this river suddenly slowed to a trickle? This is the mighty Colorado, a legendary blue streak running through one of nature's wonders of the world, the Grand Canyon. And this is a man-made canal carrying some of the Colorado's water through the desert of Arizona. It's part of the Central Arizona Project, built at a cost of $4 billion to supply the growing water needs of the state's largest cities.
You might remember that compact I told you about. That was a total failure of law, where the Colorado River was divided illogically. That's what they're referring to here. And they're about to forecast how the Colorado River's loss of water would be devastating, and climate change has definitely affected the amount of water in the Colorado River.
Including Phoenix. Like most users of the Colorado, the residents of Phoenix regard their water as something that will always be there. It's almost beyond imagination to think that global warming could take a lot of that water away by the middle of the next century. Just on the outskirts of the city, there's a grim reminder of what much of Phoenix and the entire Southwest would look like if it weren't for the water from the Colorado. Peter Glick.
The Colorado River is the lifeblood of the Southwest. By most standards, it's not a very big river, but it's just about the only water in the southwestern part of the U.S. The Colorado River is used for power. It's used for irrigation water in the United States and Mexico. It's used for drinking water in Phoenix and Los Angeles and San Diego.
Peter Glick is a leading authority on the world's water resources and on the threat to those resources posed by global warming. Today, he's at Lee's Ferry, Arizona, working with the federal agency that keeps track of how much water is flowing down the Colorado. Official measurements have been taken here ever since 1922, when the river's water was allocated among the various users. Today, every last drop is spoken for, so precise readings are crucial. The amount of water passing by is calculated from the rate at which the propeller blade spins. If this propeller ever slows down, the users of the Colorado will be in trouble.
0.2, 30, and 46 seconds.
30 revolutions, 46 seconds.
Right.
Global warming could permanently slow down that propeller blade. And that's because the small streams which feed the Colorado come mainly from the Rocky Mountains, where some climate models predict a decrease in snowfall. On top of that, even if the temperature rises only a couple of degrees, the many reservoirs along the river would lose huge amounts of water from additional evaporation. To make matters worse, higher temperatures would also increase demand. All this would mean some hard choices.
If there are decreases in flow in the Colorado, we have to decide who's going to get cut off. Arizona in particular is fairly low in the pecking order, and California is fairly high. We've also promised water to Mexico as part of their allocation of the Colorado. They are at the very end of the river. Do we short Mexico? Do we give Mexico a little bit less water so that we can continue giving U.S. users their share? Do we short U.S. users and give Mexico their full share?
The same hard choices might have to be made for major rivers worldwide that are also being used to capacity. Many flow through several countries, and this could be a prescription for disaster. The Nile, for instance, crosses Ethiopia and Sudan, then flows to the sea through Egypt.
Egypt has already said that it's willing to go to war over the Nile River. Just like the Colorado is the lifeblood of the Southwest, the Nile is the lifeblood of Egypt. There's no other water there.
Rapid change to ecological systems we now depend on. That's the threat of global warming. Having to find new places to grow crops, or new crops to grow where old ones won't. Having to protect thousands of miles of coastline, or relocate millions of people. Having to cope with a change of climate that's coming much faster than any other climate change before. Steve Schneider.
15,000 years ago, the ice age began to break up. There was ice sheets literally a mile high over New York City, across through the Great Lakes, over most of northeastern Canada and parts of Europe. And over the next 10,000 years, the ice disappeared. Sea levels rose 100 meters, 300 feet or so. Forests moved thousands of kilometers. Literally, the ecological face of the planet was revamped. It took 10,000 years to warm the planet up only 5 degrees Celsius, about 9 degrees Fahrenheit. And we're talking now about change on that magnitude in a century. So we could be modifying the climate and the whole Earth's environmental system at a rate something between 10 and 100 times faster than nature. And that's guaranteed to have nasty ecological surprises.
The sense of urgency Schneider and other climatologists feel is largely based on their computer models. Yet it's possible these models are too pessimistic, because they can't handle some factors which could dramatically alter the pace of change.
Here comes the mixed up part for number 8.
University of Chicago climatologist V.L. Ramanathan recently jumped into the middle of a controversy when he asked, what could happen as the oceans get warmer?
As the oceans warm with the rest of the planet, the moisture evaporated from the ocean will increase, just like you see the vapor coming out of this hot coffee cup. Now, what happens to this vapor as it rises into the atmosphere? It can form clouds, just like you see clouds forming on this cold glass.
Clouds influence the Earth's temperature in two opposing ways. On one hand, they reflect sunlight back into space, shading the Earth's surface and cooling the planet. The thicker a cloud is, the greater its cooling effect. On the other hand, clouds create their own version of a greenhouse effect. They form a blanket over the Earth which traps heat. The higher a cloud is, the more heat it traps.
There's a lot of clouds right over the Indonesian monsoon region, where we saw a lot of...
Using computers and satellite data, Ramanathan has determined that on average, clouds today cool the Earth more than they warm it. On this basis, many skeptics suggest extra clouds will stop the world's temperature from rising. But Ramanathan says it's more complicated than that.
If this increased cloudiness is going to be low, thick clouds, that can have a cooling effect and sort of counteract the greenhouse warming of these pollutants. If, on the other hand, this increased cloudiness is going to be upper level but thin clouds, they can trap enormously more heat radiation and sort of amplify the greenhouse warming, which I consider is a very disturbing but plausible scenario. The fundamental issue is any combination of the cloud systems can form, so in a sense the future of the planet relies on how the cloud distribution is going to adjust to the heating of the ocean.
That guy speaks so clearly, and I love his facts, but he's perfectly backward on a critical detail, so check your notes. Hotter planet, more water vapor is easy. That's not conjecture. As the planet has an average higher temperature, a known percentage of water lives as vapor instead of liquid, because in a hotter planet you're pushing more water over the edge. Okay. More water vapor is going to make more clouds, right? And clouds do have a greenhouse effect because water vapor is a greenhouse gas. They also have a cooling effect because ice crystals are shiny and so they reflect sunlight. But high clouds have more ice in them, so they're more shiny, so they reflect light.
So high thin clouds?
High clouds, which to us look thin, because they're spread out over a larger area, high clouds reflect away sunlight. They cool the planet. And low clouds tend to hold more steam, which is a greenhouse gas. So kind of like having a blanket closer to your skin, you feel yourself heating up more quickly. If you get into a giant sweatshirt, it doesn't feel like it's getting warm, but if you put on kind of a form-fitting sweatshirt, you can feel your heat right away. Low clouds trap more heat. By the way, in the last 35 years, we've also answered the mystery of which cloud becomes more common. We know that on a hotter planet, we are getting a lot more of the low clouds positive feedback, and a lot less of the high reflective clouds, which would have helped us cool down.
So the impact of extra clouds could go either way. But now consider another complicating factor that can't do anything but make the situation worse.
You know this one.
Buried just beneath the floor of the Arctic Ocean,
You know
and
that.
also beneath the Arctic tundra, are vast quantities of a substance that could cause
Called?
the world's temperature to
Called
rise
what?
much faster than the models are projecting.
Yeah.
The substance? Methane hydrate. A combination of methane gas and frozen water. It may look like a snowball, but this is 90% methane, a potent greenhouse gas. If global warming thaws the tundra and warms the oceans sufficiently, huge amounts of this gas could be released. There are many other complicating factors like these. They could make things better or worse. Climatologist Steve Schneider.
It might not be 3 degrees warming that we're looking at. It might be only 1 or 2. But if there's a 50% chance that we're going to be less than we think, there's also a 50% chance it's more. Maybe it's going to be 3 to 6. So what we're really doing is we're taking a coin and flipping it. And on one face it says moderate climate change. The other face it says unprecedentedly large climate change. And in my value system, that's not the kind of gamble I like for the planet.
Over 20 billion tons of carbon dioxide and other greenhouse gases now go into the atmosphere every year, a rate which has been growing steadily for the past 2 centuries. Eliminating these emissions fast enough to avoid climate change may be impossible, but that's no reason for inaction. The more we can cut, the less warming there'll be.
2 degrees warming is not nearly as bad as 5 degrees. And if it happens in 50 years, that's much worse than if it happens in 150 years. We can make a substantial difference in the rate of change, and it's the rate of change that is difficult for ecosystems to adapt to and for people to adapt to.
The biggest opportunity for cutting greenhouse gases lies with countries that emit the most. Together, North America and Western Europe, with about 10% of the world's population, produce about 40% of all greenhouse gases. Here, the choices of individual citizens can really make a difference. In the United States, for example, switching to cars that get 50 miles a gallon, double the current average, would cut U.S. greenhouse gases by 3%. Lester Brown.
The real question now is not how large a car that you and I can afford, but what the planet can afford. And the answer is the planet cannot afford very many gas-guzzling automobiles. Or if we're buying a house, how much insulation does it have? And if we were to insulate it better, not only how much would we save on the heating bill, but how much would we save on carbon dioxide emissions?
If all U.S. homes were well insulated, that's another 2% reduction in the nation's greenhouse emissions. Some solutions go beyond individuals. Today, the prices of coal, oil, and gas are misleadingly low because they don't include the potential cost of damage from global warming. But adding in this cost through a tax on fossil fuels would encourage conservation and also give an economic advantage to alternative fuels which don't harm the atmosphere. Generating a fifth of U.S. electricity with alternatives would reduce the nation's greenhouse gases by another 6%. Then there are CFCs. They cause a quarter of the world's greenhouse gas problem today. So until production stops, we should prevent them from escaping into the atmosphere. Venting CFCs, for instance, is still common practice in the servicing of auto air conditioners. But laws requiring recycling of CFCs could cut the country's greenhouse gases by another 2%. Planting forests could also help. New trees grow by taking carbon dioxide out of the atmosphere. So long as these forests are left alone, this carbon dioxide will never go back into the air. If the United States can plant an area about the size of Delaware, less than 1,000th of the country's land, That would soak up yet another 2% of the nation's carbon dioxide emissions. These 5 measures alone, 5 solutions among dozens possible, already add up to a 15% reduction for the nation.
There's no magic single thing to do. We need to reforest. We need to use energy more efficiently. We need to develop alternatives. We need to shape our lifestyle so we take one trip with multiple errands rather than multiple trips. Every one of these things are nickels and dimes, if you will, but if you nickel and dime long enough, pretty soon you get to half a dollar, you've got the problem half solved.
The world's developing nations also have an important role. So far, countries like China, Brazil, and India haven't caused much of the greenhouse problem. But as these huge nations strive to achieve modern standards of living, their energy use will skyrocket, and the increased greenhouse gas emissions could overwhelm reductions made elsewhere. The only way they can avoid this is by not adopting the same wasteful technologies which were used to build today's industrial countries, and that will require financial aid. As well, they'll need to control population growth. At current birth rates, the population of all developing countries combined will increase by nearly 4 billion over the next half-century. So many additional people will make the job of cutting the world's greenhouse gases even harder. Challenges like these will surely put world leaders in uncharted waters, creating the need for unprecedented levels of international cooperation. But the alternative to bold solutions will be a climate change that's catastrophic.
I'm very concerned because this is not a trivial change in the climate. This is going to cause, for me and my children and my grandchildren, enormous changes in their lifestyles. And I'll be gone, I won't be here, but they will have to deal with it.
What we now have to think about is how we can all become environmentally active, because we all have a stake in the future. We all have a stake in the future habitability of the planet.
If we're not willing to slow the rate of climate change or to stop climate change at all, we better be willing to deal with the impacts that climate change is going to bring. The changes in water resources, the changes in agricultural productivity, the changes in sea level. It's one or the other.
I only have like 7 minutes, but there's an animation in another movie that I really want you guys to see. If you could switch to questions 60 to 64, I'm going to see if we can get to it. I've got a bad feeling, but I want to try.
Anybody have?
Put on the same paper.
Yes, it's the same assignment.
The Senate.
There's all this wacky 80s LA stuff, which feels really personal because that's when I came to the US, but I think I'll just have to skip that one. You guys have no idea what a trip it was coming from my universe to this one. Okay, hold on. I don't know if I'm going to get the timing right. I just got to try this from around here.
That make the lifestyle possible. 12 million people live in the Los Angeles basin, a 13,000 square mile area bounded by mountains. The mountains act as a natural trap for polluted air as it accumulates. This dramatic time-lapse view looking down from the mountains reveals what happens to Los Angeles air on a typical day. 8 a.m.
First of all, we're going to get back to this in a separate lecture. Remember that we're talking not climate anymore, this is different. But the mountains around Los Angeles are like a bowl, and that's important. And I need to point out that smog is temporal, meaning it's a problem that pops up at a part of the day and is gone another part of the day. Anybody who knows Mexico City, Rio, Los Angeles, Beijing, cities that have smog, you wake up in the morning at sunrise, it's beautiful. 10 or 11, it kind of kicks off and all of a sudden you have smog. 4 p.m., 5, 6 p.m., it starts to dissipate and break up. By sunset, it's gone. Go.
Oh, did you, the mountains are like a bowl?
They are. They trap pollution. It's like filling a bowl with milk. And we'll explain how that happens in a future lecture.
Okay. and God eats it.
The drive to work has begun. Factories and businesses open. Polluting gases start to build. It's a summer day, and by mid-morning the gases are trapped under the usual warm inversion layer. There's no doubt by noon, it's another smoggy day in Los Angeles. As afternoon wears on, enough gases have accumulated in the basin to reach right up into the mountains. It'll be late evening before the smog breaks up. And then tomorrow, Los Angeles residents will go through the whole cycle once again.
Good days and bad days. It's a temporal thing. Smog is not a permanent condition. If you shut off all the electricity and all the cars for one day, Los Angeles has perfectly clean air that day.
Or the hill in the morning, it's like a blanket. It is so disgusting. I tell my husband, don't breathe today.
What I really hate about it is it makes my eyes burn.
When it's smoggy, it makes you embarrassed that people come to visit here.
Just want to sit down and not do much. It takes a lot of the steam out of you.
Yeah, we have pretty mountains, and with the smog, it covers it up, and you want to see them, and it looks really disgusting.
Yet, these problems stem from the typical modern lifestyle. The Matz family prepares to meet another polluted day living in the center of Los Angeles. Don and his wife, Judy, leave for work at different times and in separate cars, as does their older son, Scott. So 3 people contribute 3 cars to the 3.5 million on Los Angeles highways during the morning commute. 2 hours a day commuting on ever more crowded freeways. There's a higher price tag attached to the California lifestyle than when Judy was growing up. After the war, Los Angeles' growth really took off. When the freeways opened in the 50s, the air was already showing signs of stress, as chemistry professor Jim Pitts recalls.
The real impacts of what we now call photochemical smog really began to appear in the late 40s. They appeared in several ways. 1, eye irritation, tearing. 2, cracking of rubber. One could have one's fishing boots, and they would crack in the matter of months, or one's rubber tires, and that was an interesting phenomenon. And then the crops. Los Angeles, when I grew up, was surrounded by field crops of all kinds, lettuce, orange groves, and so forth. The crops were being impacted by something, and it wasn't clear what it was.
Plant scientists couldn't recognize any disease in this crop damage, so they began looking for some kind of corrosive agent in the air, perhaps the same thing that was causing such widespread eye irritation.
The public were furious. They want to know what is it out there, what's forming it, and how do we clean it up.
The most obvious suspects were the highly visible emissions from industrial smokestacks and backyard garbage burning. But after local government began to control these in the 50s, the bad air persisted. Around this time, a Dutch organic chemist at Caltech, R.E. Hagensmit, was working on the problem. In laboratory experiments, he'd seen how a gas called ozone caused the same kind of plant damage occurring in the fields. The mystery was nothing around gave off much ozone. It must be forming indirectly from other gases in the atmosphere.
I'm going to go right to the bell with this because there's a good explanation coming up. Please look up. Ozone is shaped like H2O, but it's 3 oxygens, no hydrogen. It's called O3. And it's shaped like H2O, the bunny ears. Ozone, up high, is a good thing for humans because it blocks ultraviolet. So up there, it's nice. It forms naturally. We've destroyed it. It recovers on its own. Ozone's a good thing up there. Fun fact, though, it's nice that we live here because ozone is hella toxic. When the smog problem started, people realized that smog includes ozone, which is toxic for us. And the fun fact is, we don't give off ozone. There's no human activity that makes significant amounts of ozone. What we do give off is the ingredients that react to become ozone. That's called secondary pollution. it's a vocab term in this unit, where we make the ingredients the primary pollutant, and those play together in the atmosphere to become something different, that's ozone a secondary pollutant. If we had a way to move our ozone 30,000 feet in the air, we would be healthier and we would have less skin cancer too. But unfortunately, when our chemicals react down here, they stay here, and that's bad for us. It's the same ingredient. We like it where we don't have to breathe it because it blocks the ultraviolet. We don't like breathing it because it's really, really, really dangerous. Yeah?
He mentioned photochemical smog, but didn't really define it.
And that's okay. We have a study goal and unit about that coming up, assignments about that.
So he started experiments on combining gases, including the ones from cars.
We had a hunch that let's take hydrocarbons from cars and oxides of nitrogen, let's put them together and see what happens. He put them together, nothing happened. Then he said, aha, we have a sun in Southern California, around the world in the summertime. Put an artificial light on, ultraviolet light, and bingo.
Ozone is made from car emissions plus sunlight. We'll come back to this.
Jose,
That's how ozone is made.
in our group, we need to be doing a seminar to check all the things.
Yes?
So we should all just drive our cars in the night.
Yeah, actually that would help a lot. Goodbye, children.
Huh?
I don't need no burritos today. Thank you if you were planning to go.
Oh.
No, I gotta do that